This is a video for AQA Further Pure Mathematics, Calculus Section 6.3, Surface Area of Rotation in Cartesian form. This diagram shows a curve from A to B which, if rotated, is going to produce a bell-shaped object. And in previous videos we've seen how we can calculate the volume of that by considering it as a sections of rectangles which are rotated to produce cylinders that we can add together. Here, however, we're looking at the surface area, so it's the arc delta S which we're rotating to produce a band with surface area. The radius of that band will be y, and so it has a circumference 2 pi y. The area of the band, we can call that delta A, will therefore be approximately equal to 2 pi y multiplied by delta S. And if we take the sum of all of those bands, we get that A is approximately equal to the sum 2 pi y delta S. It's then a limiting process where delta S approaches 0 and the summation becomes an integral to give us that the integral is the integral of 2 pi y ds. Now I can change that into an integral with respect to x, as long as we have to then multiply by ds by dx dx. In a previous video we saw that ds by dx was equal to the square root of 1 plus dy by dx all squared. This is using Pythagoras' theorem in a limiting process again, and therefore we can substitute that to give the final expression for area being equal to the integral of 2 pi y, and then the expression for ds by dx is the square root of 1 plus dy by dx squared. So normally that's written as the square root, as the power half of that expression. And that we would have to integrate between the limits of x from a up to b. So the area then is found by an integral of 2 pi y ds, but we can change that to an integral with respect to x by putting in ds by dx, and then these are evaluated between x equal to a and x equal to b. So if we've got y as a function of x, then we can substitute into this equation for y, and we can find dy by dx and substitute into this square root here, dy by dx all squared. Once we've done that, we should end up with an integral that we can evaluate. So let's look at that with a specific example. So here we have a straight line which is y equals x over 2, which is going to be rotated about the x-axis to produce a cone, and we're going from x is equal to 0 to x equal to 4. So we're going to calculate the surface area of this cone using calculus. The area will be equal to the integral from a to b of 2 pi y, and then the expression inside square root is 1 plus dy by dx all squared. That will be dx. So we need to find expressions to substitute into here. Y we know is x over 2, so therefore dy by dx is equal to a half, and then on substitution the area will be equal to the integral from x equal to 0 up to 4. 2 pi y is x over 2, and then inside the square root 1 plus 1 half squared. That can be simplified firstly by cancelling 2, and then realizing that this bracket here is 5 over 4, and therefore when we take the square root, it becomes root 5 over 2. So the area will be root 5 over 2 multiplied by pi, and all that's left inside the integral is x dx. So when we evaluate that, get root 5 over 2 pi, and then multiplied by 1/2 x squared, evaluated between 0 and 4. So in total, when we put 4 into there, we're going to get 1/2 of 16, which is 8. So, and when 0 goes in there, we get 0. So we get root 5 over 2 pi multiplied by 8, which is 4 root 5 pi. So in general then, if we've got an expression for y, then the area is given by this expression, this integral, so we can substitute for y and dy by dx into here, which produces an integral which hopefully we can evaluate. Now in this particular case, because this is a cone, you could have done this of course by using formulae that you know for surface area of a cone. However, this method can be used to prove those formulae. That concludes this video. In the next one, we will be looking at finding surface area of rotation when we've got the function in parametric form.